right, good morning. We have homework that is due on Friday, which is in 2 days. This is on Chapter 5. I was just wondering if anybody had any questions on the homework. Yes?
For number 15, it is a countercurrent, but what part is the countercurrent?
Well, it's not really a countercurrent problem, because a countercurrent problem, you would have flow in the pipe in one direction and flow going back on the outside in the other direction. So I wouldn't call it countercurrent, but it is flow in a pipe with the outside just kept with zero concentration. So it's sort of half the countercurrent problem, just the inside of the pipe, and ignoring or the artery and ignoring the vein, you could say, in the one we did in class. But the mathematics of how you derive the differential equation are very similar to that countercurrent problem. Other questions? Alrighty. Then we also will have, we're going to continue talking about Chapter 6. There will be another homework assignment due a week from Friday. And then our second exam is 2 weeks from today over Chapters 4 to 6. You will have similar practice exams. We'll have time to review. But Chapter 6 is a pretty big chapter, and we'll be talking about that for the next few days. All right, so the first thing I want to do is I want to review what we figured out about the nerve membrane, and we represented it as an electrical circuit. And this, in fact, is Figure 1 from the Hodgkin-Huxley paper that I emailed all of you. What is really how they figured out how nerves work. So, there's a circuit. This is the outside, this is the inside of the cell of the axon, and this is going to be the membrane, and the various ways current can cross the membrane. One of them is there's a capacitor. So you have current crossing the membrane through the capacitance. Obviously this is not direct current because capacitor acts like an open circuit to DC current, but AC currents can charge and discharge the capacitor, and you end up getting a current through that branch of the circuit. And then there was 3 types of ion channels. First of all, we had sodium channel. So this resistor, we usually represent it by a conductance, the sodium channel conductance. And it has gates that can open and close. So we draw a line through this resistor, meaning it's a variable resistor. And then you have a battery, which is the Nernst potential for sodium, which is positive inside, so the long side of the battery is on the inside. And you also have potassium, that's the other major ion in this model. It's also a variable resistor. Its battery goes the other direction. And then you have this small leak current, which is just a single resistor that's not variable. And it has its own battery, which is V leak. And that is our electrical circuit. Now, we can represent this as an equation for the current across the membrane. So the membrane current, I'll call it IM, it's really current per unit area, is going to be a capacitive term. And remember, you only get current through a capacitor if voltage is changing with time, plus GNA, and this is V. V again is the voltage across the membrane, minus VNA. So notice if the voltage across the membrane is the same as the Nernst potential, then you don't have any current going through the sodium channel, no matter what its conductance is, because sodium is essentially in equilibrium. Plus GK, V minus VK, plus G leak, V minus V leak. So, what we need to do is we need to explore some of the implications of this equation a little more. Now, if there's no stimulus current, if you're not applying a current, you're going to have no net current across the cell membrane, and therefore this IM will be 0. And so this will just become a differential equation for V. Now, warning. I sent you all the Hodgkin-Huxley paper. It's a great paper, But it's got one problem, and that is they use a different sign convention for the voltage than everybody else in the world, and in the book, our book that you're using, and what anybody talks about. So let me just draw the conversion you have to do. This is the Hodgkin-Huxley paper. In Hodgkin-Huxley, they define the resting potential to be 0. So in other words, the resting potential of the nerve isn't actually 0, but they measure all voltages with respect to rest. So in their model, V rest is 0. And that's one change. And then if they depolarize the membrane, that is, they bring it up towards what we think of as the sodium Nernst potential. So that's called depolarization. They call that a negative change in the voltage across the membrane. So essentially, they're considering the inside grounded and the outside being the giving you the voltage across the membrane. And if they hyperpolarize, which would bring it to the sodium Nernst potential, or plus 12 millivolts, that's called hyperpolarize, it becomes a positive change. Everybody else in the world does it this way. So everyone else has the voltage across the cell membrane is actually minus 65 millivolts. That is, outside's grounded, the inside is negative. So you get minus 65. And if you make the inside positive relative to the grounded outside, you go up to about plus 50 millivolts. And if you hyperpolarize, you go down to about minus 77 millivolts. So these scales, they're really all the same except for two differences. First of all, they define the rest scale difference. And second of all, Hodgkin-Huxley have a minus sign compared to everyone else, where depolarization is negative for them and depolarization is positive for us. So the only reason I'm telling you this is because if you're reading along in the Hodgkin-Huxley paper, which I think would be a great idea, and it doesn't seem like it's quite the same as what I was telling you in class, it may well be because of this sign convention. So I guess you just get a big beware. That's the bottom line of what I'm talking about. Okay. Now, next thing I want to do is I want to take a look at what happens during an action potential. First, we're going to take a look at it from sort of a point of view of a cartoon, and then we'll try to do something a little more quantitative. So first, let's do our cartoon. And we're going to start at rest. And remember what we found. Here's the membrane. It's the bilipid layer, and it has a potassium channel, and it has a sodium channel. And the potassium channel had an N gate, a gate here that can open and close, that we called N. And the sodium channel had an H gate and an M gate that's closed at rest. So it looks like this, where this is the potassium channel, this is the sodium channel. And that's how we looked at it last class. Now suppose somehow you depolarize the cell. That is, you make the inside a little more positive. Maybe you do that by taking an electrode and injecting current to the cell. Maybe that happens because some depolarization downstream diffuses in, and we'll talk more about that in a later class. Somehow, the inside of the cell, depolarization raises it maybe 10 or 20 millivolts. What happens? So you're going to raise V, and here's what's going to happen. First of all, there's some rules to remember about these gates. N gate and H gate are very slow. They take several milliseconds to respond. So immediately nothing happens to N. And immediately nothing happens to H, because they're just too slow to respond quickly enough. However, the M gate is fast. And the M gate has the property that M opens upon depolarization. So M opens upon depolarization. So if you raise the voltage, it'll cause M to open up. Now what's going to happen now that you have the M gate open? What does it look like is going to happen?
Sodium's going to flow in.
Sodium, there's nothing stopping sodium from flowing in. This is the sodium channel. Sodium's going to come flying out here, and there's a lot of sodium channels, and once they get open, that becomes dominant. Sodium comes out and raises the potential out here. It carries its positive charge to the outside, leaving the chlorine inside, or whatever the anion is, to charge up the... So you end up getting a depolarization. So, you find what you create is a positive feedback loop. So let's see how that works. Here's your voltage across the membrane. If you raise the voltage, that causes M to open up. Now why does it cause M to open up? Apparently in this protein that's represented by the ion channel, there's some charged gate that responds to the electric field across the membrane and causes some piece of the gate to swing open and let the current through. So you let M open. If you let M open, that causes sodium to enter. Sodium enters, and sodium, being a positively charged ion, is going to cause the voltage across the membrane to increase. So, you get voltage increases, causes them to open, causes sodium to enter, causes the voltage to increase, and it goes around in this loop. And you have a positive feedback, a vicious cycle. So what happens is if you get to the point where this vicious cycle starts, you get sort of an explosion of transmembrane potential, and you get an action potential. So the upstroke of the action potential is when you get this rise because of this positive feedback loop. Now, what do you think would cause this feedback loop to stop? I mean, it sounds like it's going to cause... Keep going. Why doesn't the voltage just go off to infinity and you have a big spark and the membrane burns up and you know what would stop this feedback loop?
It reaches sodium's potential.
It reaches the sodium Nernst potential, because in that case, if the voltage gets up to the sodium Nernst potential, this term will go to zero. So in other words, even though M opens up, that'll no longer cause sodium to enter. So what you get in the action potential is you're initially at rest, minus 65 millivolts. Here I'm going to plot voltage versus time. And then somehow, maybe by a stimulus, it starts to rise and it starts that feedback loop and it goes up to approximately plus 50, which is about the sodium Nernst potential, and it stops there. And that's the underlying part of the action potential. So, then now what? Now it sits there at top. What causes it to eventually fall back down towards rest? Well, there's two things. Okay, first of all, we said H and N are slow, but they eventually will kick in. And H closes upon depolarization. But slowly, and by slowly I mean time constants on the order of maybe 3 milliseconds or something like that. And also, N opens upon depolarization. With anything even slower time constant, similar but a little slower, maybe about 5 milliseconds. So, you now have this picture, and now H begins to close. So let's see here. There's the two gates. M's still open because the voltage is still high, but H will begin to close. And that'll stop the sodium. And N, which was partially open already, is going to open completely. So I'll just draw it as if N was sort of partially closed here, partially open, and now it's wide open. And that's going to cause potassium to come back in, carrying its positive charge, which is going to then cause the inside to... What have I done? No. Potassium's in here. This is the inside. There's a lot of potassium on the inside. It causes it to go out carrying its positive charge, leaving ions to make it drive it back down negative. So after you get the action potential, it will slowly turn off as H closes, shutting off the sodium, and N opens up wide, opening up the potassium completely. All right, so you're turning off the action potential. Suppose this gets back to rest. Now what happens? Now you're back here. The voltage is back to the resting potential. But N, which is slow to respond, is still wide open, and H is still closed. M can respond quickly. Once this gets back to rest, M will close. And you have a situation like this. So this is when it's gotten back to rest. Now what's different between this and our initial state?
H is still closed.
H is closed. So suppose you were going to try to stimulate another action potential and you try to raise the voltage, maybe with an electrode. You start this, you'd cause M to open, but you wouldn't cause sodium to enter because H is still closed. So it breaks the feedback loop. So this is what you call refractory. That is, it won't respond to a stimulus. Nerve cells are refractory until finally H, which closes upon depolarization, will finally open back up. And N will go back to its sort of half-open state. But H will finally open up, M will be closed, and you get back to your resting state where we started. Now one more thing. When this is in this state, N is wider open than usual. Now if you remember, the resting potential was set by, so there was the potassium Nernst potential, which was way down at minus 77 millivolts, and you also had this leak current, which isn't real big, but at rest, N sort of halfway closed, so it was actually big enough that the resting potential was sort of halfway between the potassium Nernst potential and the leak potential. During the refractory period, the potassium conductance is even larger, which tends to drive the action potential down to a little bit hyperpolarized until it finally goes back. So sometimes we call this the hyperpolarized section, as well as the refractory part of the action potential. They're kind of different concepts. One has to do with just the value of the transmembrane potential. Refractory has to do with the state of the gates in the membrane. And then eventually it goes back and reaches its rest back to where it started from. It'll just sit there until you stimulate again somehow. So this is our cartoon explanation about how the action potential works. And even if you don't remember some of the math that we're going to talk about next, hopefully you'll remember this sort of explanation. It's basically sodium coming in and then potassium going out. So sodium coming in here, potassium going out here. If you had a time scale on this picture, it would be something like 0, 1, 2, depends a little bit on the temperature. That's sort of the time scale in milliseconds. So the whole action potential is over in just a few milliseconds. That's in the squid nerve axon, which swim around in cold water. In humans, it's very similar. We don't see this hyperpolarization section very prominently. And in humans at 37 degrees, all mammals, this tends to, the whole thing's over in about a millisecond. But it's basically the same physics. It's the same main two channels that are causing the action potential throughout all animals. And really throughout both nerves and skeletal muscle. Okay, so questions on the cartoon version of the Hodgkin-Huxley model and how it works. Okay. Yeah.
So for the raised V, you have sodium going out, the cartoon above.
Yeah.
Yeah. So you have sodium coming out in the
Ah.
cell, or does it come?
Okay, I screwed up, didn't I? I screwed up. That's probably why I screwed up here, because I screwed up here. There's a lot. This is the outside. This is the end. There's a lot of sodium out. I'm sorry. So it would come in and bring its positive charge. Oh, for crying out loud. Okay. Thank you. That's the way the picture should look. Sodium coming in, bringing its positive charge inside. Glad we got that straight, otherwise I would have gone back and re-recorded the whole lecture, because that's a major error. But we have that straight now. Okay, sodium coming in initially, charging up the inside positive, then potassium going out, bringing the inside back to being negative, is the basically what happens. And remember, we saw last class, it doesn't take much sodium to come in, and it doesn't take much potassium to come out. So you don't really change significantly the concentrations of sodium and potassium in one action potential, which means you can do this thousands of times before you begin to affect your concentrations. And in the background are the pumps pumping away, but at a really slow time scale, hundreds of milliseconds, seconds, just maintaining the concentration gradients where they started, no matter how many action potentials require. Okay. Other questions? All right. Then, yes?
So I'm thinking that when sodium comes into the cell, it is positively charged on that side of the membrane.
Yes.
Why doesn't the positive side just push it again towards the outside?
That's because, well, it will. It will, in a sense. That's what eventually stops this, is once the electric field builds up, and so it's the electric field pushing it out, it will eventually reach the equilibrium where sodium won't come in anymore. And the voltage will be at the sodium Nernst potential. So basically what you're saying, you're describing what happens right up here at the peak. Sodium won't come in. It's still going to want to diffuse in because of the concentration gradient, but now you'll have the electric field pushing it out. They'll be in balance, no sodium movement at all. You sit right here at the top of your action potential. But during this part of the upstroke, the electric field won't be big enough to buck the diffusion, and sodium will still come in. Same thing really goes for down here at potassium. Eventually, you'll just about reach the potassium Nernst potential, and it won't be coming out as much. But during the recovery phase of the action potential, you get a lot of potassium coming out. Okay. So, yes. Anything else? All right. What we want to do is we want to look at all this a little more mathematically. So I'm going to erase all this, and then we'll analyze it in more detail. Before we jump into all the math, let me just tell you a little bit about Hodgkin-Huxley. They both started working on this in about the late 1930s. Hodgkin was a little bit more senior, Huxley a little more junior. And they started working, and then in 1939, war breaks out. They're in England. England goes to war, enters the Second World War. We didn't enter until 41. England entered in 39. They basically had to put all this aside, and they both went off and did war work, working on radar, working on submarines, and then came back after the war, restarted up their research, and by the late 40s, they had basically come up not only with a qualitative explanation like we just made, but they developed an entire mathematical model that describes what's happening, and they were able to verify that against experiments. So that's really why they got the Nobel Prize. So let's look in a little more detail here. Sodium current. Well, we have to figure out how these gates opening and closing enter our description of what's happening. So here's the sodium current. It's going to have GNA bar. What's that? That is the conductance of the membrane to sodium if all the sodium channels have all their gates completely open. So if you could somehow give a drug that would just open all the gates in the membrane in the ion channels, you'd have this GNA bar would be your conductance. Then you have M and H, and in fact this is M cubed H. And finally, what we had before, V minus VNA. Okay, this term is what we had before. If your voltage is equal to the Nernst potential, you're in equilibrium, and there's no movement of sodium no matter what happens. It's these things, H and M, these gates, that are an interesting new thing. And the gates are now interpreted as mathematical quantities. So before I talk about the gates, let me just review. VNA is about 50 millivolts, and GNA bar is 120, and the units they use is millimole per centimeter squared. It's a conductance per unit area. What's a millimole? A mole is the reciprocal of an ohm. Notice it's just ohm spelled backwards. So a millimole is really a 1 over kiloohm. Nowadays we would call it a Siemens. A millisiemen would be the same as a unit of conductance. So, and we have M and H. M and H we now think of as mathematical variables that vary between 0 and 1. 0 means the gate's completely closed. 1 means the gate's completely open, and it can have any value in between. All right, so we need to have some description of how M and H behave. So Hodgkin-Huxley came up, and the one thing you have to realize about their model is not like some fundamental physics model where you actually have a model that describes the basic fundamental behavior. Their model is sort of an exercise in curve fitting, coming up with some equations that seem to describe it well without understanding what's really happening at a very fundamental level. So they assume that M obeys this equation. The MDT equals M infinity, which is a function of voltage, minus M over tau M, which is a function of voltage. Okay, so how do you interpret this equation? Well, whenever you see something like the MDT, what you're really saying is, how does M change? M changes by basically these two terms. If you didn't have this term here, you'd have minus M over tau M. So M would decay away. But you do have this term here, M infinity. So if you were in steady state, which at rest potential you're in steady state, M is just going to equal M infinity, because the MDT is 0. So you can think of M infinity as the value of M that M is going to move towards, and it's a function of voltage. And tau M is the time constant, and it's also a function of voltage. So the only thing that makes this complicated is the fact that these quantities are a function of voltage. Otherwise, this is exactly that same equation that we saw multiple times, including objects falling under gravity with friction or Newton's law of cooling. We've seen this variety of cases. But we need to know how M infinity, in particular, changes with voltage. So we said that M opens upon depolarization. So they did some experiments, which we'll talk about probably next class. And they found that M infinity obeys, looks like this. This is going to be as a function of voltage in millivolts. This is about minus 100, minus 50, 0, plus 50. This is going to be using R notation. So rest is minus 65. And depolarization, the top of the action potential is out here at plus 50. M is closed at rest. So that means it's 0, essentially here at rest. M opens upon depolarization. So when you get out here at depolarized potentials, M is approximately 1. And M goes something like this behavior in between. What this says in words is M opens upon depolarization. You can find a plot of M infinity in a Hodgkin-Huxley paper if you look at figure 8 on page 516. But remember, everything's going to look a little different because they define their voltage scale opposite. So it'll probably look like a mirror image with the voltage shifted. But it's essentially the same physics. M infinity, now tau M also depends on voltage, but it's not so important. Tau M voltage dependence is sort of a detail that if you want to do the actual calculations you'll worry about. But for the most part, tau M is on the order of half a millisecond at its fastest. So, or I guess at its slowest. So tau M is very quick. Half a millisecond, it gets over fast. H infinity, on the other hand, is different. H infinity, it goes between 0 and 1, minus 100, minus 50, 0, 50, voltage across the membrane in millivolts. H is partially open at rest. There's rest. So H is maybe 0.6 at rest. H closes upon depolarization. So out here at depolarized potentials, it's closed, and it goes something like this. It heads up to 1 if you get down here at hyperpolarized voltages. So that's H infinity, and again, tau H has some time voltage dependence, but it's not crucial. Tau H is on the order of several milliseconds. We'll just say about 5 milliseconds. Could be a little shorter in some cases. All right, so what we now have is a description of, by the way, M not only obeys this equation, there's a very similar equation for H. So this is a little more of a mathematical description of the sodium current. Now, these equations, these expressions I've just drawn are actually Hodgkin-Huxley. This is where they really did the curve fitting. They just found some exponential equations that were kind of complicated that they could fit to make these quantities look like their experimental data. So there's a whole bunch of equations that will eventually give M infinity and H infinity and tau M and tau H as a function of voltage that we care about. You may need to use in some of the homework assignments. I'm not even going to try to write them all up here on the board because it gets kind of long-winded. And remember, the whole thing's multiplied by V minus VNA. So again, if you're out here, if there's really no voltage that has both M and H open at the same time in steady state, but if you can work things out so M and H were both open, maybe with some weird drug, or you get then the whole, these would both be 1, and GNA bar would be your inductance. Questions on the sodium channel? Oh, one more thing. Why M cubed? Why not just M? That's actually a very interesting question, which we're going to try to answer later. But the M cubed was, again, just pure curve fitting. It's almost as if there's 3 gates in series, and they all have to be open in order for M to be working. We'll come back to why M cubed. These are nonlinear equations, in part because of M cubed, but even more because of these weird functional dependence of M on V in a very strange nonlinear way. So they're going to be nonlinear differential equations. Okay, let us go and look at the potassium current. IK equals GK bar N to the 4th power V minus VK. So it looks a lot like the sodium, except it only has an N. There's nothing like an H variable. There's only one gate it is raised to the 4th power, and I promise we're going to explain why we use these weird powers. May not be today, but we'll get to it eventually. And VK is minus 77 millivolts. That's the potassium Nernst potential, which is very negative. GK bar is 36 millimole per centimeter squared. It's quite a bit smaller than sodium, so if all the gates opened up, sodium has a bigger conductance than potassium. But if you start closing some of the channels, potassium can end up winning. Okay, and finally, there's an equation for the NDT, which is exactly the same as for the other gates. And all we need to do is figure out how N changes with voltage. So we really need to look at N infinity between 0 and 1, minus 100, minus 50, 0, 50. This is voltage in millivolts. And at rest, N is partially open. So N is somewhere, here's rest, and sort of part way open. N opens upon depolarization. So if we make the voltage go positive, N opens, it'll eventually go up to 1. None of these gates ever go larger than 1. But it goes down, and then it falls and goes back down. If you hyperpolarize, you really close off N completely. So it looks like that. And tau N, again, depends on voltage somewhat, but it's approximately several millivolts, say around 3 milliseconds, around 3 milliseconds. So you end up with curves that look like that. So the N looks a lot like M, but H is the odd one. M and N are what you call activation gates. They open upon depolarization. H is an inactivation gate. It closes upon depolarization. And then finally, the leak current, which is really easy to describe. And leak current is I leak equals G leaked, which is just a number, times V minus V leak. And G leak is 0.3 millimole per centimeter squared. Now notice, this is real small compared to the sodium and the potassium and the sodium. So like I said, this leak voltage is really a small little current. It's going to result in small currents. The only reason it's significant at all is if you have M, H, and N all sort of closed, close to 0, then since leak has no gates, you can eventually get, it can eventually become significant. So at rest, it's not completely negligible. And V leak, the Nernst potential for the leak channel is minus 54.387 millivolts. Now, this is what you'll find in their paper. Why in the world did Hodgkin-Huxley give the leak potential to 5 significant figures? Well, the resting potential of the nerve actually comes out of this model. You can calculate what the resting potential is. It's not an input parameter anywhere. And they knew that their resting potentials were about minus 65. So this whole leak business is kind of a big fudge factor. They wanted to figure out how to make the resting potential about right, and they found that if they adjusted this leak Nernst potential to this exact value, the resting potential came out to be right at minus 65. So it was really the ultimate fudge factor, which they just did for curve fitting. So that explains why. Okay. Now, questions about this sort of models? Yes?
So like, you said like for M and H, it's like between 0 and 1.
Yes.
Like I noticed that you didn't put like the line under, so are they never like fully closed or like fully open? So like you know like greater than or equal to, use like greater than.
Oh well, you know, these are real numbers. So maybe mathematicians care about 0.999999 versus 1, but as a physicist, it's the same. You could call this greater than or equal to if you wanted to, but for all practical purposes, it doesn't matter. Yeah.
For the leaker, is it I leak equals the G leak, or is it?
I leak is equal to G leak times V minus V leak.
And it's not G bar like the others?
It's not G bar only because there's no gates, so G bar would be the same as G leak. So I believe in the paper they didn't bother putting a bar over it. Just it kind of helps you remember then that these have the gates in front of them. But it doesn't really matter at that point. It's just a symbol. Other questions about this? Okay, I'm going to erase all this and I'm going to put up kind of a summary of what we have so far. All right. Okay, so we have the current, which again is 0 unless you're stimulated. It has these 4 paths. dV dt plus GNA bar m cubed h v minus VNA plus GK bar v minus VK plus G leak V minus V leak. Now, I have some good news and bad news for you. The good news is that on the next exam, you don't have to memorize this whole expression. It's not going to be one of the equations you have to memorize. But the bad news is you do have to understand it. If I give it to you, you have to be able to use it. Yes?
Where's the N4 for the GK?
It is forgotten. Thank you very much. N to the 4th. V minus VK. Good. All right. And then there are 3 equations for M, H, and N. V minus H over tau H and dN dt equals n infinity of v minus n over tau n. And you have these 4 equations, and you also have some equations telling you how m infinity, h infinity, n infinity, and technically how the time constants all depend on voltage. And those are extra equations. So it's not really 4 equations, but it's essentially 4 differential equations, plus some equations that express how these quantities depend on voltage. So, what the Hodgkin-Huxley model is from a mathematical point of view, it is 4 coupled differential equations. In each case, especially if you set I equals 0 and then just solve for dV dt, you're going to get dV dt or dN dt, dH dt, dN dt is equal to some function. And it's a nonlinear differential equations, in part because of h and m to the 3rd and n to the 4th, but mainly because these functions depend on v in a very nonlinear way. They're coupled because this equation for dV dt also depends on m, h, and n, and the equations for m, h, and n all depend on v through these functions. So they're all coupled, nonlinear differential equations. You cannot solve these types of differential equations analytically. Only in extremely special cases can you do that. So there have to use numerical methods. Now picture yourself as Hodgkin-Huxley. Back in the late 1940s, early 1950s, they essentially didn't have big computers like we do. Huxley was the guy who did all the mathematical calculations. He had one of these hand calculators where you punch the numbers in and you pull the crank and then it tells you what the multiplication was. And in order to solve these numerically, you have to write the derivatives as differences. V t plus delta t is equal to v plus t all over delta t in discrete steps, and then calculate forward step by step. So I had to do hundreds of these calculations on this hand calculator. So he wanted to calculate one action potential. It took him like a week of doing these calculations, but he eventually was able to make these calculations, really some of the first big biomathematical calculations in the field of bioengineering or mathematical biology. Then the other question that we really want to get to is, how did they come up with this? How did they get the data that underlies all these equations? So their great accomplishment was twofold. Number one, it was coming up with this mathematical model. But number two, it was getting the data they needed to formulate the mathematical model. So that's the next thing we're going to talk about. We'll start talking about it today, and we'll talk a whole lot about it on Friday. But before I go forward to talk about their experimental techniques, any last questions about their mathematical model? Now, you guys are lucky or unlucky, depending how you look at it. In this class, you're not actually going to have to go through and perform numerical calculations. For a small plug here, in about a year, not this winter, but I think the following winter, I'm teaching my graduate level bioelectricity class. And if you want to take that class, one of the projects is to go through and do these numerical calculations in a program like MATLAB or C++ or something. It's not terribly hard to do, but it's just a little beyond what we have time to do here in this class. The book does contain a computer program that does the calculations, but it's written in some old language that you probably don't use anymore. Okay. Let us now start talking about the experimental side of things. All right, so here's your nerve axon. Remember, this is the squid giant axon, so you can stick electrodes down in it. It's big enough to be able to do that. And what you want to do is you want to be able to measure and determine how the conductance changes across the membrane as a function of voltage. So they had to develop some technique. It wasn't completely their development. There's also people in the United States who are working on this, but it's called voltage clamp. And they were the first ones to really use it and show its power. So how does voltage clamp work? Well, you have to stick two electrodes into the nerve. So you stick one electrode down into the nerve, and out it comes, and it goes to a voltmeter, just to measure its voltage. And outside is ground, so you're measuring the voltage inside with respect to ground. And then there's another electrode, which goes to a current source. So, you measure voltage, you control or you inject current. Now, the idea about voltage clamp is what you do is you say, okay, I want the voltage to be held at some constant level. So you watch the voltmeter. And if the voltage starts to deviate from that level you want, you adjust the current source. So you might turn the current on, you might turn the current lower or higher. And you do that in order to maintain the voltage constant. This is a feedback system, negative feedback, much like your furnace does. It measures the temperature. If your temperature starts dripping down, it turns the furnace on and brings it up. If your temperature gets hot, it turns the furnace off. Same thing here. You are controlling through negative feedback, maintaining the voltage constant. So you're clamping the voltage. Now, you want to do that on a millisecond time scale, so you can't just sit there and watch and tweak the knobs. What you have to do is you have to develop circuitry that can do this feedback. And the circuitry they use are those things called operational amplifiers. Nowadays they're all solid state. Hodgkin-Huxley's time they were more vacuum tube devices. But they're devices that essentially can measure voltage and adjust current to keep the voltage fixed. So they were able to do this at a time scale on the order of milliseconds and clamp the voltage. So let us see an example of one of their experiments. But before we do, remember I sent you the video of Young's dissection of the squid? I'm going to send you another video. And this video shows people doing voltage clamping. And it's pretty fascinating because Hodgkin actually appears himself in the video. They got the nerve, they hung the nerve sort of vertically, and they lower the electrodes in, and they give you a close-up of what the electrodes look like. It's a very nice video. It's only maybe 4 or 5 minutes long. So I do want you to watch the voltage clamping video to get a feel for how these experiments were performed. Okay, so here's a typical voltage clamping experiment. First of all, we're going to specify the voltage in millivolts. And let's see, here's a minus 50, plus 50, 0. This is time. Let's call this 0, 5 milliseconds, 10 milliseconds, milliseconds. Okay, initially, before you start the experiment, the nerve's sitting at rest. You don't have to inject any current for rest. It's just minus 65 millivolts. So then you want to begin your experiment. You're going to say, okay, I want to raise the voltage across the nerve up to some level and then hold it and see what happens. So they took the nerve and they raised the voltage at time 0 immediately up to, say, plus 15 millivolts, and then they held it for a long time. And then they wanted to watch and see how much current they needed to pass through their current source, which they could translate. Well, they basically measured the current they were injecting. So, what's going to happen? Let us see the current, which is in milliamps per centimeter squared, and 1 minus 1, 0. I should give you a warning. If you look at these data in the Hodgkin-Huxley paper, they show this kind of data, but again, their voltage scale is different, their current scale is different, and that what's going in versus out is defined with a minus sign. So the pictures will look similar, but not the same. Okay, let's see, 0, 5, 10, 9 milliseconds. No current's required to keep this nerve at rest. So initially, current 0. The nerve is just at rest as if you had no electrodes in there. What happens at t equals 0? You change the voltage. What happens when you change the voltage? Which of those terms in that, remember we had the picture of the electrical circuit with 4 legs. Which term is going to get really big when you abruptly change the voltage? Well, that capacitive term, the current through a capacitor is C dV dt, the rate of change. The rate of change is almost infinite here, and you change it very, very quickly. So you get initially a huge spike, which is the capacitive spike. So there's always going to be this giant spike right when you turn the voltage on. The capacitive spike you're not really interested in. You know how capacitors work. You don't learn anything. And it gets over very quickly because once this becomes flat out here, the current through the capacitor is back to 0. So you just get this giant capacitive spike which sort of shoots off the display, but then it stops and you can ignore it. So we'll ignore the capacitive spike. Even if I don't happen to draw it in some of these figures, it's always there. Now, let's say the nerve's at rest. What happens when you depolarize? What's going to happen to the gates? What gates open? M gate opens, and it opens rather quickly, and the H gate's already open, so sodium will rush in. Sodium represents a current. Positive charge coming in by the normal sign convention is going to be negative, so you're going to have a negative current. Then it's eventually voltage interaction potential. Eventually this would stop because the voltage would reach nurse potential, but you're holding the voltage at minus 15, so the nurse potential is up here. So it's never going to totally stop until the H gate finally closes. H closes upon depolarization. So H will close, but with a time scale on the order of a few milliseconds. So there's the sodium current turning off. Now, how about the potassium current? The potassium current turns on, it opens up with voltage, and there's nothing to turn it off. So your potassium current is going to slowly turn on, and you're going to end up getting a current that looks like this and stays on. So you can sort of see the current trace. This is what you really measure. It looks like this. And they interpret this as sodium inrush and potassium going out. Now, you can't really divide this up into what's happening with sodium, what's happening with potassium. You just get a total current. But you can try other experiments. For instance, there is a lot of potassium inside, sodium outside. You can replace the sodium with some other ion. You can replace the sodium so it has 0 sodium out here. And so there's no way you can get a sodium inrush because there's no sodium. Now, what happens if you take all the sodium out? It goes osmotically completely out of whack because it no longer has the 300 millimolar, milliosmol osmotic pressure. So you replace the sodium with something. They usually replaced it with like sucrose or some sugar. The sugar is way too big to go through these ion channels, so the sugar just fixed the osmotic problem, but had no role in the way the ion channels work. If you do that, take the sodium out, you then get a curve that looks like this. You still get this big thing, but now you have no sodium inrush, and the potassium then will slowly turn on. So this is no sodium. So I've sort of told you the story like we know, but it's the way it worked with Hodgkin-Huxley is this is how they figured out that sodium was the current that came rushing in. Because when they took it out of the bath, they got rid of this. So they said, aha, there must be this sodium current rushing in. Now, the peak of this kind of tells you what GNA bar is, and it also tells you a little bit about the dynamics of the gates, how fast M opens, because this is going to depend on how fast M opens, how fast H closes, and it tells you a lot about the peak value of N, because this really tells you the size of the potassium current at long times. So you can do this kind of experiment. Then you can subtract this curve, dashed curve from the solid curve, and what's left is going to be this curve, which is just the sodium. So you can experimentally, you can figure out what's the sodium, what's potassium. It's a little difficult to replace the potassium because that's inside the cell, and you'd have to actually replace all the fluid inside the cell. Eventually people figured out how to do that. Eventually people could make a little roller that would squeeze all the salt water outside, and then they'd fill it up with a new solution, and they could make measurements replacing the potassium, but that was after Hodgkin-Huxley did their initial work. But they could easily change the sodium in the bath outside, because that's just the bath that's surrounding the fluid. So you get this sort of behavior. And then you could do other voltages. You could do another experiment where now instead of raising it to plus 15, you raise it to 35. And you're going to find that you get a different type of current. And you can raise it maybe to minus 5. And you can get another experiment. And if you do all these different voltage clamp experiments, eventually you have enough information to trace out those whole M infinity, H infinity, N infinity curves and figure out how the experiments work. So this is the voltage clamp experiment, and we're going to talk a little bit more about this next class. But we'll go into a little more detail. In particular, it's not real clear how you get the H-gate dynamics, and that has to require some explaining. But at least you understand the basic idea of voltage clamp. People do voltage clamp all the time nowadays. It used to be you had to have a great big axon in order to stick wires down the inside and make these measurements. But they've since developed these little glass pipettes that you fill up with a conducting solution, and you pull them so that they have a point that's a tip that's like a whole 1 micron in size. So you have a glass pipette that looks like this. You fill it up with some big solution as a conductor, and this is about 1 micron. And then you just bring that down, you poke it into the nerve, and you can make measurements, you can pass nerve currents directly into a nerve axon. And then the cell can be really small. It can even be spherical. You don't have to stick wires in it. You just poke electrodes in it. So this is the way it's done in pretty much modern times. Is they use these glass microelectrodes, and they can then do voltage clamp experiments and learn everything they want about the behavior of the nerve. So that is where we stand with Hodgkin-Huxley. We will continue on and talk some more about Hodgkin-Huxley model, and in particular about some of the figures from the paper on Friday. Okay, homework is due on Friday also, so remember that. And if you haven't gotten old homeworks or exams back, I still have them here.